Good morning, ladies and gentlemen, boys and girls of all ages. Hope you guys are having yourself a great start to your week. Today we are going to talk about intersections and unions, and back into our probability with independent and dependent probability. And so, one thing I want you guys to remember is that intersections and unions for us today should be a review that an intersection would be something that is both A and B. A union is something that is A or B. One of the easiest ways to see this is through Venn diagrams. Now if I have A and B and they're represented with a Venn diagram, well, the intersection for this one would be this spot right here. Now, that would be an intersection. With a union, however, that if you had A and B, that would be everything. Because it doesn't matter if it's A, it doesn't matter if it's B, it just wants to be everything. Now, the way to calculate that is the intersection, well, the union is equal to the probability of A plus the probability of B minus the intersection of A and B. And it has to be minus the intersection of A and B because you don't want to count the spot in the middle twice. Count it twice would be very bad. So, if we have something like probability of A union B is equal to 7 over 8, or 7 out of 8. The probability of A is 5 out of 8, and the probability of B is 3 out of 8, meaning that if this happened 8 times, I would get it probably about 3 times. Talk about that in a moment. We want to figure out what the intersection is. Now, ladies and gentlemen, remember, any sort of probability is what is the number of things that you're looking for over the total number of things that exist. Now, for this case, if we just set this up into this equation, we have 7 over 8 is equal to 5 over 8 plus 3 over 8. Is equal to something. Oh, not equal to something. I need to change that. Minus some value over 8. Now, why over 8, you say? Well, this being our intersection, it's probably going to have the same denominator of the other things, so I'm just trying to make it easier for us. Well, if we do the math, that means 7 over 8 is equal to 8 over 8, because 5 plus 3 is 8, minus n over 8. Well, if you subtract 8 over 8 on both sides, that's going to give me a negative 1 over 8 is equal to a negative n over 8. Get rid of the negative signs. Your intersection is equal to 1 over 8. Now let me get rid of this n and just say that this is the probability of your intersection. Probability of A intersect B is equal to 1 over 8. And the way we got that is we combined the probability of our A and our B into one probability, subtracted it from the union. And the reason we are able to do all this is because everything is built into this equation. This equation is always true. Alright, so look at this one. The probability of A union B is equal to 3 over 5. The probability of A is equal to 7 over 20. The probability of B is equal to 1 over 4. We want to find the intersection of A, B. The probability of A and B. Now, what's different about this question? Well, the first thing I notice is that they all have different denominators. We have a 5, a 20, and a 4, so we're going to have to change some numbers up. But if we put things in the proper order, we can notice that it's not that hard. Well, if we know that probability of A union B is equal to the probability of A plus the probability of B minus the intersection well, we know that the union is 3 over 5. A is 7 over 20. B is 1 over 4. And this is something. I'm just going to keep that probability of A intersect B. So, one thing we probably want to do here is try to get a common denominator, because if we get a common denominator, we will be able to put all of these together without any difficulty. Now, a common denominator between 5, 4, and 20 is going to be 20. Remember, if you have a denominator, or if you're trying to get a common denominator, you can't get the number smaller, the numbers can only get bigger. It's like trying to find the least common multiple. Well, what's the least common multiple out of all of these? Well, it's this one. 5 times 4 will give you 20. And if we have that, well, what do you multiply 5 by to get to 20? Well, it's 4. Well, what's 3 times 4? Well, that's going to be 12 over 20 is equal to 7 over 20, since this is the one that didn't need to change. Now, what did you multiply 4 by to get 20? Well, that's 5, so that's going to be 20 on bottom. And what is 1 times 5? Obviously 5. If we combine these two, and we add this on the other side, A intersect B, we see that we get 12 over 20 is equal to 12 over 20 minus the probability of A and B. Well, if we subtract this on both sides, well, that gives us 0 is equal to the probability of the intersection. Now, ladies and gentlemen, this just means that there is no intersection. If your probability of some event is 0, that event doesn't happen. It can't happen. So if there can't be, if I can never land on this intersection, if it's a Venn diagram, well, that means the intersection doesn't exist. So that's what's special about this one. And we could figure that out by doing our math. Alright, independent probability. There are two events A, and I wanted to go back and talk about independent probability again because it's always a good refresher course. Especially if you're talking about different events. What's the probability of rolling a die and getting a 6, rolling a die and getting a 6, and flipping a coin and getting heads? Well, when we consider these, we have two different events. Two different types of events. We're not doing the same thing twice, and getting different results, but we're doing two entirely different things. So, since they are entirely different, all we have to do is consider their individual probabilities and multiply them together. Now, what's the probability of rolling a die and getting a 6? A normal cube die has how many sides? 6. And how many times does 6 appear on them? Only once. Now I'm going to multiply that by the probability of flipping a coin and getting heads. Well, how many faces does a coin have? 2. Well, how many of those are heads? 1. So the probability of rolling a die and getting a 6 flipping a coin and getting heads is 1, since 1 times 1 is 1, and over 12, since 6 times 2 is 12. Our probability is 1/12. Now, let's see how that's different from this one. Oh, it looks like we're doing two of the same event, but we're rolling 2 dice with different conditions. Probability of rolling 2 dice and getting an odd number and a number that is less than 3. Now we would consider this to be an independent probability because the 2 dice are acting independently and they have different conditions. What the first dice gets is not what the first die gets, isn't going to affect what the second die gets, theoretically. We're not going to talk about whether or not the dice will hit each other. So, let's consider the probability of getting an odd to the probability of getting less than a 3. Let's say that this is my little less than symbol. It is not a heart. Alright, probability of getting an odd number. How many numbers can you get on a die? 6. How many of them are odd? 1, 3, 5. So we have 5. And how many numbers are less than 3 on a die? Well, we've got 1 and we have 2 out of 6. So we multiply these together, we get 10 out of 36. You can simplify this by dividing by 2, and it is 5 out of 18. Oh, woohoo! I nearly made a mistake. It is definitely not 5 out of 18. How many dice? I said 5 as my last one, but there's only 3 of them that are odd. Well, 3 times 2 is 6 out of 36. You divide those both by 6, and it's 1/6. So, you actually have a greater probability of rolling 2 dice and getting an odd and a number less than 3 than rolling a die and getting 6 and getting heads. Alright. A bag contains 2 coins. There are 5 pennies, 2 quarters, and 3 dimes. If you grab a coin from the bag and replace it, what's the probability of getting a quarter and a dime? In that order. Should add it in that order. Well, there's 10, you know that there's 10 coins. And you've got 2 events, so you're going to do 2 of them. Probability of getting a quarter and probability of getting a dime. Now, ladies and gentlemen, it's definitely important to say that we replaced it, because if we did not replace it, this would be a dependent probability since our numbers would change. It'd go from 10 coins in a bag to 9 coins. So how many quarters are there? Well, there's 2 quarters. And if you want to simplify these before you do your multiplications, it's totally fine, that's up to you. I don't think it's necessary. There goes one of my cats. And so 2 times 3 gives me 6. 10 times 10 gives me 100. If I want to simplify that, I have to divide both sides by 2. Numerator would become 3. Denominator would become 50, and that is your simplified fraction. So, if I were to draw 2 coins, and I replace it after the first one, and I wanted to get a quarter and a dime, well, that would be 3 out of 50. Because, well, we did the math. But this 3/50ths, which is a funky fraction to say, means that if I did this experiment 50 times, I would only get a quarter and a dime 3 times. And that's it. Ladies and gentlemen, tomorrow we're going to talk more about dependent probability and a few other subjects. I hope you all have yourself a wonderful